Right presentation. Thank you very much. Okay. So first of all, it's great to be here. Thank you for the invitation to Christina, who couldn't be here, obviously, and to Patrick to present here. I am European, as someone said before. Yes, I'm representing Deakin University as well, although I did leave early this year. I chose to retire from Deakin to spend more time in Europe at POLYMAT, but also to do a startup, to hearing before about startups. Because I think it's really important that as a professor, we almost, in Australia, we have a problem in terms of encouraging younger people to take risks in looking at taking the science into a startup. So Patrick Howlett, who was my collaborator, Deakin, and myself, began a company called Donati Energy, which is a sodium battery startup looking at high energy density sodium. I won't talk about that today. I'll talk about polymer electrolytes today. But I just wanted to say, to follow on from some of what was being said before, that we have to think about the future of where we're going in terms of battery technology. It's not just about EVs and stationary storage and grid storage. Batteries are ubiquitous. Everything that we use, if you like, has batteries. And one of the areas that we want to focus on with Donati is at the agri-tech sector. It's so important that we look at automation, precision engineering, data banks. So much it requires novel, safe, high-energy batteries. So think about when you're doing your research, it's not just about doing a battery for an EV or for stationary storage. There's so many applications out there. So for the younger people, think about the science that you're doing and where it might apply in the future, not just the present. So I am coming from San Sebastian the last few days. I love the place. That's why I'm spending more time in Europe. And I'm going to talk about some work that has been ongoing between Australia, Deakin University and POLYMAT for almost a decade now, since Professor Mercedes David came to visit us at Deakin about 8 or 9 years ago. So how will we? Let me see if I can get this working. Okay. What am I doing wrong? Help. Sorry, it's being recorded as well. Why? Right. Okay. Thank you. That's what I pressed. Thank you. Right. So what's the context of why I'm talking about polyionic liquids as electrolytes? I think we all understand now that to really achieve high energy density batteries, safe batteries based around, say, lithium or sodium metal or other metal alloy, we need to look about the solid state configurations. Now, there are a lot of complications in solid state batteries because we have to think about an electrolyte that will have high enough ionic conductivity. I've got room temperature there, but actually it can be high temperature. It doesn't have to be room temperature for many applications. We also have to consider the contacts between the solid and the electrode, both at the metal side, but also within the context of the cathode. The interconnectivity of the cathode materials and the electrolytes is very, very important. How do we achieve that? So there are lots of material choices, and the majority of people tend to use, I think, what I've seen from the industry especially, ceramic or glassy electrolytes. And the reason for that is because very much to do with their high conductivity and their stability. However, I guess since my early postdoc in 1990, I've been working on polymer electrolytes, and I believe that actually is a really important class of materials for solid-state batteries. And we have, as I'll show you today, I hope, there's an enormous chemistry and composition space that we have available to us to really design new systems. This could include ionogels or gel materials as well. And a lot of you know me from my ionic liquids work, which I won't talk all about today. But we will talk about polymer electrolytes based on polyionic liquids. That'll be my main focus of today's talk. And I'm still having difficulties here. Right. Okay. So I thought I'd put this slide together, complicated slide, to show you again the broad range of composition and chemistry space that we have in polymer electrolytes. See if I can get this to work. Yes. So this is a very simplified ternary phase diagram. So in a polymer electrolyte or in electrolytes, we typically look at this region here where we have a solvent, might be an IL, it might be carbonates, glimes, whatever that happens to be. And we add salt, and we have our traditional electrolyte that we have in our lithium-ion batteries, for example, or other sodium-ion batteries too. We have we might use polyionic liquids, which might be lithium or sodium single-ion conductors, for example, and we might add a solvent to try and improve the ionic conductivity of the key ion, lithium or sodium, in this direction. Oops, this direction. And then we have a polymer where we add salt. Now, the polymer can be either a neutral polymer, traditional polymers like PEO, polycarbonates, where we add salt, and we find we have, again, large composition range. We know that the conductivity, the TG, all these are affected by this composition. And then we also have the possibility in here of having all three of these things. So the polymer, the solvent, the salt, to control both the conductivity, the mechanical properties, the glass transition temperature, the stability, all those things are available to us. A lot of the current solid state batteries that are present are really based on gel systems, which might be the PVDF, HFP, for example, system where you have a solvent and a salt embedded in that. And they're dubiously called solid state, I think. I'm more interested really in looking at the region. Again, let me see if I can get here. The region today in particular, I'm interested in looking at the region here, where we're going to focus on the polyionic liquid as a potential matrix to dissolve salt in, to show how good a matrix it is, and to show it's not just an inert matrix. It actually can be very, very important. The chemistry can be very important to determine the properties of the material. And we're going to look at adding salt, and we're going to focus on the high concentration range here. Some of the previous work we did looks also in the region where you add some solvent as well to improve the properties potentially. But we have a lot of space to play with. So, and we say in Spanish, vamos a ver. Let's go and see what we can do in that space. When I was showing this to one of my postdocs actually at POLYMAT, he said, it's a very complicated talk. You have to give an overview slide so people can follow you. So this is my overview of what I'm going to talk about today. I'm going to start off, I'm going to focus very much on a polymer that was, sorry, I'm having to use a polymer, which, there we go, polydadma, which is a material that was introduced to us through David Mercedes. It's a material where the charge is actually on the backbone. Many of the previous polyionic liquid systems have the charge hanging off the backbone. And I think what we'll find is that what we found actually is that when the charge is in the backbone, it can have very different properties, particularly in terms of stability, electrochemical stability. So we're going to look about the early work on adding salt to this and what do we see in this system. We're going to look at empty simulations quite a lot today and trying to understand the ion structure and transport as we add different salts to this system. We're going to then look at what happens when we add an asymmetric salt, which itself can become quite glassy if you quench it. What happens if we add an asymmetric salt to the polydadma to get high salt solubility at high performance. Then we're going to move into more on the empty simulations to look at, well, can we use mixed anions to enhance sodium solubility in this polymer? Because sodium salts we're finding very difficult to dissolve in ionic liquids and polyionic liquids. So we'll investigate that possibility. And then we're going to look at early work on changing that nitrogen to phosphorus, to phosphonium system, and see what impact that has on the polymer electrolyte. And finally, all of these materials that we make, I'll show you very early on, be very honest, are not very solid initially. When you add the salt, they're quite soft. And so we're going to see, well, how can we make these better by looking at block copolymers in the system. I did have a last dot point here, which is going to be anionic polymers, but I took that away thinking I wouldn't have enough time. So that's for another time. Okay, now with overview in mind, let's get going. So the question we have to ask then is, that we asked ourselves back in 2015, 2016, when David came to join us, is can this polydadma, which is quite an interesting material, you can buy it in the chloride form, you can substitute different salts, different anions to get different polymers. People here in Münster have also done this work. Monica Schoenhofer did some work on this early on as well, as a pure polymer. We want to know, are these systems possible as matrices for dissolving a salt, and what is the result in terms of electrolyte? We focused on TFSI, bisfluorinated anion, and FSI, because we know those materials tend to give, those anions, give us good SEI formation, solid electrolyte interface formation, which is very important when we're looking at lithium or sodium metal batteries. So we start off with these systems, but we're moving towards looking at other systems as well. In fact, this slide I put up on purpose because one of the students who's here, a co-tutor student between Deakin and POLYMAT, Dr. Anna Clara Orlando, she got a PhD a few months ago. She looked at substituting non-fluorinated systems into this polydadma, including these two phosphates, for example, and we've got some borates as well, organoborates, to attempt to make water-soluble binders, functional binders, which have been shown to be very promising. And I encourage you to go and look at her poster if you want to know more about those systems over the next couple of days. So the beauty about the system is we have a large, again, range of compositional space. We can change X to be pretty much whatever we want. We've tried default, we've got DCA, tetrafluoroborate, we've got these phosphates. So lots of possibilities, and all of these change the properties of the polymer itself, but also change the properties of how well we can dissolve salts in that polymer and how those materials behave as electrolytes in batteries. Okay, so the initial work then that Dr. Sean Wang, who was a postdoc in my group, and now he's a professor in Dalian in China with Chinese Academy of Sciences. He investigated what happens when we look at the DADMA TFSI or FSI, and we dissolve a lot of salt. Now, what I'll say is what we're looking at here is not the low concentration of adding salt to a polymer like we do in PEO. We're looking at what we call the polymer in salt complexes. So it's like a solvent in salt where the dominant composition or dominant component is the salt, and the polymer is acting sort of as a secondary component, but a very important secondary component. So here we see that when we added 1 to 1, so 1 mer unit of the polymer to 1 LiTFSI salt component, that we form a material that's actually quite brittle, not really very nice material, but quite high TG. So we kind of discarded that, and then we looked at what happened. We mixed the anions TFSI, FSI 1 to 1 again, and we see, independent of whether you start with a TFSI polymer or the FSI polymer, when you have 1 to 1 TFSI, FSI anions, you get a TG of around 2 degrees. The material is softer, it's still quite brittle. When we have the homoanion FSI, FSI, we see TG decreases. So in this case, those of you who know about polymer electrolytes from PEO, for example, polycarbonates, what we find usually is as we add more and more salt, the TG goes up and the conductivity goes down. In these systems, as you add more and more salt, the TG goes down and the conductivity goes up to a maximum, to a point, which we'll talk about in a moment. Based on this work, we decided, and I note here that the polyIL itself has a TG that's around 100 or more than 100. Very hard to measure the TG of this particular system by DSC, and I'll talk about that a bit later on as well. So we started off then looking at these homoanion systems, and let's see where we go. So I should say, I'm sorry, I probably should have said earlier on that the TGs that I showed you the previous slide on this slide, they're derivatives because the TG is so hard to measure in the system. So we take the derivative to find where the TG is. So what we see here is we look at the effect of adding different amount of LiFSI to the polydadma FSI system. And we see that here we have the 2 to 1 is basically 1 mole of monomer to half a mole of LiFSI, and that TG, so that TG is 2.2. Then as we add, whoops, so that is what happened there. Then we add the 1 to 1, the 1 to 2, so TG goes down. And on this side here, we see that the conductivity is going up, but only to a maximum of about 1 to 1.5. As we go beyond that, we start to decrease the conductivity again, despite the fact that the TG has still gone down. So this was a bit perplexing initially, and I'll show you why that is in a moment. And I'll show you that with some modelling that Dr. Fang Chen has done for us. As I said earlier on, these materials, I won't lie, these materials are quite soft. And so in order for us to do a more robust, to be able to do this characterization of materials in, say, a cell, we incorporate them into a PVDF spun mat, which is about between 50 and 100 microns. And then we form these nice squares or self-standing membranes that we can do further testing on. But we are working towards, I'll show you at the end, working towards making these freestanding without having to add anything else. So just to try and explain why we got the conductivity decrease, we had a much more careful look at the DSC traces. And here what we have, there we go, can you see that here? No, sorry, I'm struggling with this pointer. What we have on the left-hand side is the DSC traces for the various compositions, and we see that the black, red, and purple trace up to 1.5 is just a TG. We see the 1 to 2, we see a TG there, but in the as-made material, we do actually see a couple of other transitions, which are indicative of other phases forming the material, and we see that much more clearly as we go to higher salt concentration. Now, this is not the LiFSI crashing out of like precipitating in the polymer. It's actually new phases being formed. And those of you who can remember the PEO-based systems, and you look at the old Colin and Vincent book on polymer electrolytes, you'll find that PEO with salts forms multiple phases. And so I think this is what's happening in this system. We're forming different phases of the polyIL with the lithium salt. And that's also clear to us when we look at the NMR spectra on the right-hand side for the different compositions. In the magic angle spinning for lithium-7, we see multiple lithium sites. Lithium has a very narrow chemical shift range, but nevertheless, we can see that different sites are appearing. Now, so this means in the polymer itself, in the electrolyte, we have multiple environments for the lithium. And in some cases, this environment gives you optimum conductivity. In other cases, we lose some of that dynamics. So let's go further and see if we can understand what's going on here. We're also very lucky enough to have at Deakin a strong NMR team, which I sort of established about 15 years ago now with Luke Odell, and we have a pulse field gradient diffusion measurement device, which allows us to measure multi-nuclear diffusion measurements. So here we have lithium for the system I was just showing you. We have on the top here we have the diffusion coefficients at 80 degrees Celsius, a high temperature here, of the lithium and the FSI anion. And we see that as the composition increases with lithium FSI, the diffusivity goes up initially and comes down again. We also see, in this case, unusually compared to the PO-based systems, that the lithium diffusivity is higher than the anion. This would translate supposedly into a higher apparent transport number. Now, we're not measuring this under electric field, so it's under just normal diffusion measurements, normal diffusion conditions. And so, so we are definitely seeing that we have a higher diffusivity for lithium. And when we do the ratio of lithium to anion diffusivity in the purple bar graph, we see that we have an optimum at around 1.1, 1:1.5, which marries up with the optimum conductivity that we see. So can we understand this further? So in this measurement, then I don't have a lot of battery slides in this particular talk, but here is one that we do show the performance of these membranes that I showed you before with the optimum composition. We see, if we look at the bottom left-hand slide there with the transport number measurements that we measure using Bruce and Vincent technology or techniques, we see that the 1:1.5 indeed gives us the higher electrochemical transport number measurement, as well as the highest ratio of diffusion coefficients we saw earlier on. So we're getting now more than 0.5, 0.56. In all three of those systems, we're above 0.5, but that 1:1.5 gives us the optimum transport number in this system. We see on the top left-hand side that the lithium symmetric cell measurements are very, very stable, hundreds of hours with low potentials. We are doing this at 80 degrees C. Remember, I said at the beginning, we're not just looking at EV batteries or other batteries. There are many applications where high temperature is important. And sometimes you have to target those unusual applications with the materials which you have available to you. And here we see a blow up, if you like, of the symmetric cycling. And of course, we put this into a reasonable battery with 1.1 milliamp hours per centimeter squared. Sorry, this is the wrong hours here. And LFP at this time, but we have also done the NMC equivalent. And we get good stable stability, good stable performance at this temperature under these conditions. So that was promising. But we now want to step back and understand what's going on. Can we improve this further by understanding what's going on in this system? And so in this case, we have Dr. Fang Chen, who was a postdoc with me more than 10 years ago, and now has her own team within Deakin, a computational team. And one of our students is here from visiting from Lyon, and will be also giving a poster, I believe, through Hari. So what can we learn from using MD simulations? And this is a snapshot of a lot of work. This is published in also part of the Joule paper, the original Joule paper. So what Fang did here was set up a simulation box using, I think it was Gromax in this case, she was using, with a number of polyiol chains, about roughly 12 or so monomer units long, so not super long, but long enough. And then she was adding different amounts of salt and looking at the conformations, the structures in these MD simulations, and trying to understand if there was a correlation between these and what we were observing in the data. What she found in these systems is there was always three different types of coordination environments predominant. There was the polymer FSI, and the polymer FSI or TFS or whatever the anion is that you have, that polymer anion polymer interaction is what controls the TG of that polymer. It's almost like a virtual cross-link. So that is a very important interaction, which is broken down as you add more lithium salt, because now what you end up having is a lot more polymer FSI lithium co-coordination environments that dominates in that region of the optimum conductivity and transport. And as you go to higher salt concentrations, you begin to get a lot more of the LiFSI phases or regions, nanoregions, and this, of course, can be quantified, and she found in her work that there appeared to be an optimum co-coordination environment of around 1:1.5, which, of course, she didn't scan every single composition, but in under composition she looked at, which correlated with the high conductivity. Can we understand that further? Well, in her Nature Materials paper, she then looked at other salts that were dissolved in the same polymer, and she looked at sodium, potassium, and magnesium. And again, in this particular paper, we were focusing on, can we correlate co-coordination environments or coordination environments and diffusivity, and can this then be linked back to performance in a real system? So here what we see is the sodium 1:2, so 1 mer unit to 2 NaFSI units, 1:4, where we've got 4 NaFSIs to 1 sodium. This is in the actual computer, remember? Potassium, similarly 1 to 1 and 1 to 2 in the magnesium systems. So what we found here was that in the magnesium systems, where the binding energy is very strong to the anion, you actually had a lot less of the co-coordination environment and more of the salt, if you like, molten salt environment. And that correlates to a low diffusivity when you measure on the right-hand side the diffusion coefficients that we calculate for the mean square displacements. And the magnesium has the lowest. And then we see that the sodium has, the 1:2 has a really high co-coordination environment, and that correlates to a high sodium diffusivity. In fact, the metal ion is significantly more diffusive here than the anion is in the MD simulation. And also what's really interesting is almost a factor of 10 higher than the lithium equivalent. So this was suggesting to us that sodium polyalcyls will be more diffusive than the lithium systems, which I'll show you in a moment that indeed they are. And the potassium would in fact have the highest diffusivity, correlating the binding energy, but that the anion and the cation here were very, very similar. So that would mean the transport number might not be as high. And what she also found in that work was that the transport of the ion, if you think about normal solvents or normal polymers, you think about ion dynamics being related to vehicular motion. People talk about hopping motion. What she found very clearly in this work, and also is true in the ionic liquids work, is that the transport of the ion occurs through a rearrangement of a cage, of the solvation cage. So you go maybe from having, say, 6 coordination, maybe in a certain time step, you might have 4, and then you join new FSI, new coordination environments join, and then ultimately you've changed the cage you're in from A to B. And that's how the diffusion occurs, through this structural rearrangement of the coordination environment. So you need to have, if it's too strong, you aren't going to have this high diffusivity. And if it's too strong, diffusivity won't be as high. But also what's interesting here is you may think about how you might modify this cage environment. And we'll talk about later on about mixed ions, or using, I think, one of the previous excellent lectures that Patrick Johansson gave online was related to high entropy electrolytes. So I wonder whether here actually we may have a similar possibility in this system. So something to think. If you have those who haven't listened to Patrick's talk, you should listen to it. It's a very good talk on various solvent electrolyte systems, where the high entropy idea of changing the environment comes into play. Okay, so then can we actually show that this works in reality? I mean, that was the MD simulations. Sean actually worked with Fang to make the materials, measure the TG, and we see that this is the lithium diffusivity, the TG, which is quite low, despite the fact that diffusivity actually is lower than the sodium. The TG actually, you would predict, should be more diffusive. Sodium has the higher TG, followed by potassium. And yet, if you look at the conductivity plot here, which has a lot of data, I'm sorry, but the majority of this data from the black here up to the blue, green, red, pink, blue, purple, blue. These are all the lithium salts with different compositions here. So the 1:2 is that pink one. The potassium is the green one, and the sodium is the yellow one. So you can see the sodium has the highest conductivity in practice, which correlates with what we measure with the MD simulation diffusivity. We can't measure diffusion of sodium using PFG because it's a very hard nucleus to measure diffusivity of, but from the MD simulations, we see the conductivity agrees. It's a factor of 10 higher in the sodium case. And indeed, when we made the cell, the transport number measurement here shows a fairly high steady state current and a very small drop from the initial. All the Bruce and Vincent method really says how much current do you lose, how much you polarize when you apply a potential. And what you see here is the more drop you have here, the lower the transport number is of the species you're interested in. So this small drop from the I0 to the I steady state says that the transport number for the sodium should be quite high. And indeed, this correlates to a very nice cycling of the cell. Now, the material here is supported on the PVDF5, but we can get some nice materials. Okay, so that was the initial work. And then recently we have a new student in the group, QAK, who's working with myself and Fang. And his interest was, what happens if I change the monomer? Okay, what if I change the monomer? What if I do something really simple, like just modify the substitution on the nitrogen? Now, in early work with looking at the polymers themselves, this was looked at just from the polymer perspective, the TG, not so much as an electrolyte. This is something we're still doing at the moment. But the polydadmer is here, then we put the butyl group, an isobutyl group, and then there's ether oxygen here. We chose the TFSI, or KOA chose the TFSI anion for MD simulations in this case, because that's all we had for experimental TGs to compare to make sure our modelling was actually okay. So now, how do we measure TG on a MD simulation? Now, usually most of us know we measure TG for a polymer or a solvent by doing a DSC measurement. That's fine, or we might do a DMTA, but you can also do it by dilatometry. You can look at the rate of change of volume with temperature, dB by dt, first order derivative, and that rate of change at that point, at that inflection point, is the TG. So in the MD simulation, we can do this. We can measure the volume as a function of temperature, and we can then take the gradients, and we can see where the TG is. Interesting for the polydadma TFSI, which is notoriously hard to measure TG in a DSC. It's also quite hard to measure it even in the volume change. It's there, but it's very subtle, and that must be something to do with the material itself mustn't have a massive change at TG, and that's something for another story for another day. But what we measure here is 392 from that inflection, 301 roughly to 290 here for this one, depending on where you take the intersection. And then when we correlate that to the TGs that were published TGs, we find in fact they're not bad. With the simulated and the experimental are pretty close. So that would give us confidence that we can use this model now to start looking at what happens when we add salt to these systems. Okay, so very happy to see that was the case, and also interesting how much lower the TG of the ether oxygen containing system is, and we'll look at that in a moment. Oops. Right. So we do again some typical characterization in the MD simulation. The two things I'll show you here are the co-coordination environment here for the lithium TFSI polycation here. Again, it dominates. The Li TFSI here, and then the polycation TFSI system here. So you can see this is the 1:1 TFSI. TFSI is not as soluble as FSI, so we've gone to 1:1 in the simulation box. So these aren't that different, to be honest, but if you look at the mean square displacement evolution here, which is what we measure the diffusion coefficient from, so the slope of this line is a diffusion coefficient. And if we look over here, we see some really interesting observations. The red is the polydadma, the one that we know and love so far. The blue is the material containing ether oxygen. So there's a huge difference. And the bold lines versus the dashed lines. The bold lines are the lithium, and the dashed lines are the anion. So two things. First of all, in all cases, the lithium ion is more diffusive than the anion, which is what we've seen both experimentally in the previous systems and also from the MD. But the trend is interesting. So here we have the ether oxygen gives you the best diffusivity compared to the polydadma, and then the isobutyl and this long chain butyl. So that was the trend from the MD simulation. Now, we haven't yet made these systems in the lab. That's the next thing for us to do is, can we make these, and can we validate, as we did with the previous system, can we validate that this actually would be a good material? And then we look at the sodium TFSI system, and this was a bit perplexing to me, still perplexing to me, is first of all that, again, there isn't, there's a bit of a difference. We see the DADMA has the most co-coordination. We see the ether oxygen gives you the most sodium TFSI clusters, if you like, or not clusters, the wrong word, coordination environments in the material. Actually, probably the isobutyl gives you the most, well, similarly the most. But when you look at the diffusivities here, two things to note. First of all, I'll go back one. The number here is 5, right? And the number here is 50. So first of all, as we saw earlier on, the sodium is 10 times more diffusive than the lithium. This is a good thing if you're making an electrolyte for sodium batteries. But also, again, the ether oxygen gives you the highest diffusivity. But now the DADMA is actually giving you a better performance, and putting a more bulky group on that nitrogen actually decreases diffusivity. And this is probably related to the ability for co-coordination, the ability to change that environment I showed you earlier. The cage environment probably is going to change, because what is allowing that sodium to diffuse, or the lithium to diffuse, is that rearrangement of the coordination environment. Okay, so I guess from that work, so far, we haven't published this work yet. It's just currently being drafted. There's a lot more detailed understanding to be gained by looking at the MD structures more carefully, looking at the cages more carefully. But so far, what we've seen is that there is a promising ability to control the polymer to control the diffusivity. So that's something we want the experimentalists in the group to have a look at next as well. Okay, so now I'm going to jump to going back to polydadma again, which is a material that we make. We have a lot of, easy to buy, easy to exchange. And now we're going to look at, okay, can we increase the solubility of lithium beyond the 1 to 1.5 in a stable way? And can that allow us to improve the conductivity, to improve the performance? And then we're also going to look at whether mixing the anions has an impact. this is what I've said here, can we use asymmetry of the ion and mixing to try and improve the performance of these materials? Okay. So this is when Dr. Shinji Kondo came from Japan on a Japanese fellowship in the group about a year or so, of 2 years ago now, actually, almost. And he worked with Fang and myself to look at making these systems with FTFSI. Now, this is a really interesting anion, and we owe a lot of our thanks to Michel Armand and his group for these FSI, TFSI, FTFSI, and all the new anions he's currently making as well, based around this system. Although fluorination, of course, is not necessarily something we want in the future. We want to try and get away from that in the future. But for the moment, we're going to look at what this FTFSI does to these systems. So on the left-hand side, we have the TG behavior as a function of concentration of salt. As we saw earlier on, the TG goes down initially from over 100 down to below 0. And the 1:2, so 1 DADMA unit to 2 LiTFSI salts. And this is actually a mixed system, so it's FSI, TFSI. We see the lowest TG, and then we see TG goes up. And that was initially a surprise to us because we didn't have the TG of this system. And then Shinji found that he could quench the salt into a glass or into a liquid or into a glass indeed, and he was able to measure the TG of the salt, of the pure salt. It's metastable, but it can be quenched and you can get a DSC of it. And he found that was above 0 degrees. And this is why we see this parabolic behavior for TG. So in other words, when we look at the effect of salt on the TG of the system, it depends very much, not just on, it doesn't always go down. It depends on what the TG of that final salt is that you've got in there. What will that be? So there's not a straightforward correlation between TG and salt composition necessarily. What was a surprise to us, though, I think was a surprise to us, was the conductivity behavior had this same maximum at 1:2. It's like, well, why? We want to get past it. We want this to go higher. We want higher conductivity, and yet we reproducibly found that the 1:2 gave us the highest conductivity by a long way, almost a factor of 10 decrease here, which when you look at the TG, it was a surprise because the 1:2, 1:4 aren't that different in TG. So it can't just be the TG that's causing this effect, right? It's got to be more than that. And it goes back to, and I haven't got time to go into details here, but it goes back into whether or not the lithium ion is coupled or decoupled from the rest of the motion of the system, right? In the molten salt, it seems to be more coupled than it is in the polymer salt system. So this again goes back to this cage environment and how that changes and the rate of change of the cage environment for a lithium ion. So that was interesting, disappointing, but interesting. We found the 1:2 was the best system, but maybe it wasn't so disappointing because it's not just conductivity that's important, it's also the transport number that's important. And so we measured the diffusion coefficients again. We measured the lithium diffusion coefficients, the green, the orange is the anion diffusion coefficients. And we see that definitely the lithium is significantly more diffusive than the anion. In this case, we see it's almost a factor of, and remember the FTFSI is a dominant anion in the system. We see that it's up to a factor of 3 more diffusive in the case of the 1:8 system. And if we then measure electrochemical transport number, as we've done on the right-hand side here, we see that although the overall steady state current goes down because the conductivity has gone down effectively, the actual transport number has gone up to about 0.8. So 1:8, which is still not a single phase, not homogeneous system, at least not on the macro scale. We see a transport number of 0.8, and at the 1:2, we see the 0.57 that we saw earlier on for the FSI system as well. So that was interesting. And the question then was, well, how well will this perform in a device? Does it perform in a device? And also, can we improve this further? And this is where again, controlling that cage environment by controlling the FTFSI coordination. We have done some modeling, but I haven't got that to show you here. But what we have here is we added not just LiFTFSI to the polydamate FSI, but we added a ratio of these two. So we controlled the FSI-FTFSI ratio as well by adding 2 different salts at different compositions. So and I'll just show you some of the data here. So what we found here is the self-diffusion of the FTFSI DADMA is this value here, and this value here is when you have 1:1, so it's 1:4:4, rather 1:8 is 1:4:4 ratio of FTFSI to FSI. So by mixing the anions, we have increased both the conductivity on this side. We've also increased the lithium diffusivity by a long way, and again, much higher, still retain the high transport number. So this material here then has in the range of materials that we tested is an optimum material. And again, if you look at the symmetric cell testing, the red values represent the truly mixed anion, the 1 to 4 to 4, and the green one represents the 1 to 8 of the FTFSI, and the 1 to 2, which is the maximum conductivity in the system, is the grey. So despite having the maximum conductivity, that's not the best performer in terms of the lithium symmetric cell over potential and the stability. You see that, in fact, the lower conductivity but the high transport number gives you the better performance in this particular case. And you can also see the stability is increasing between 1:2 and 1:8. And again, we put it into a I think it was LFP solute again. But we found that good stability. So it does work as a battery electrolyte in a lithium metal cell, solid state cell. So this is just really a small part of the composition range that we've talked about, right? We've got a lot of room to play with here, which we haven't even considered yet. We've just looked at 2 different compositions here. That this might not be the optimum. So a lot of, from the applied sense, this is where AI might come into it, I guess, a little bit more, is to help us choose what might be the optimum composition to give us the best performance in these systems. Okay, so now I'm going back into the simulation box, and I'm going to look at what happens if we start to try and dissolve different sodium salts, because sodium has been a bit of a problem for us. Some of the FSI works well, but the other ions we have found really hard to dissolve. I'm not quite sure why at this point. So we thought maybe mixing salts will help us get a better behavior. So the idea again being in the system to try and use a polycation to modulate, if you like, the behavior of the sodium ion by having 2 different coordination environments or multiple coordination environments possible here. And we've looked at the BF4, the DCA, the TFSI system, PF6, and other systems as well in this case. So what happens to this in the simulation box, the first question? Well, good and bad news. So in the MD simulation, we had Louis Meyer, who I think is now working in Ljubljana. He was a MESC student who was in our group. He's now working with Rob Domenko in Ljubljana. He was a fantastic master student who spent time in our labs in Australia. And he looked at modelling these systems, so FSI and adding different anion, right, with sodium. And we fixed the ratio 1:2 because that was, well, because that's what seems to be optimum so far in various measurements that we've done for lithium and for sodium. What we found with BF4 is we got these nanoscopic domains, phase-separated domains, and we found them also in TFSI but to a lesser extent, and we found them in DCA but to a lesser extent. BF4 definitely had these domains. But interestingly, when we actually went and measured the diffusion from mean square, this is all theoretical, computational, from mean square displacement, the diffusivity, this is now centimeters squared per second, diffusivity was significantly higher in the system. So if you could keep the system molten, you'd have a really high sodium diffusivity. Big if. And even the TFSI and the DCA showed high diffusivity compared to the just the FSI system. And so this gave us some promising idea about whether we can control the sodium transport with mixed systems. But when we actually made the materials, unfortunately, we got increased heterogeneity in these systems. So in reality, this corresponded to phase separation. But the phase separation is not necessarily, again, the salt crashing out, because we still measure DSC. We measure TG of these systems. The TG of the BF4 is significantly higher than the other systems. It might mean that, now, are we measuring TG of just the regions here, which is amorphous? Are we measuring the interfacial regions between the solid, the crystal, and the polymer? There's a lot of work in the literature that suggests that you can have space charge regions between a solid and two solids potentially. So there's a lot of interesting things to think about here in terms of how the ion dynamics might occur in these systems. You know, is it in the bulk? Is it in, or is it actually in what role does the interface play? So there's another thing to think about for the future. Measure the conductivity of these systems, even though they were heterogeneous. We see on the left-hand side that the FSI, TFSI, the black and the brown are the most conductive here, the FSI being the most conductive. The other ones aren't that bad. I mean, considering that they're so heterogeneous, we are measuring some conductivities, except for the TCM system here, which doesn't dissolve at all. So this was, again, a bit disappointing, but nevertheless, we are seeing some conductivity. The interesting thing here, going back to what is a transport mechanism, on the right-hand side, we scale the conductivity by TG to see whether or not the ion conductivity was coupled or not to the polymer TG. And what we see is that in the BF4 system is significant so at TG on T equals to 1, that's where your system is being measured at its glass transition temperature. And what we see is that we're actually measuring higher conductivity compared to what you measure in FSI. And this correlates in Austin Angel speak to a decoupled system. So there is clearly the motion of the ions, whether it's sodium or BF4 or both, is not reliant purely on the bulk dynamics of the system. There's some other mechanism taking place. That's as far as we've gotten so far in that system, but there's more to be done in that system, certainly to understand how we can use mixtures to optimize and understand sodium conductors. Okay, the last thing I'm going to talk about now, I'm getting a little bit low, but as fast as I can, is second last, is phosphonium versus ammonium. We know from our ionic liquid work, phosphonium ionic liquids give us better material properties than the polydinium. And so we thought, can we translate this into a phosphonium? So in POLYMAT, Daniel Mantione and Alex, a student, worked on how do we make this polymer. And there was one literature report for not batteries many years ago for making the system for, I think it was, might have been water treatment. And the idea being phosphorus being bigger, same periodic table, bigger, weaker interactions, it may change how the behavior of the system translates in ion dynamics and ion structuring. Very quickly, I'm not a synthetic chemist, but I want to show you basically the first most difficult step is making this monomer. And this monomer has taken Alex, where is it? This here has taken Alex the best part of 3 or 4 months or more to make and purify. It's a very hard thing to make, but it's doable. He's made a bulk amount of it now. Then you can polymerize that to make the polymer. We're still struggling to get high molecular weights, but we're getting reasonable molecular weights here. And then you can do ion exchange, but whatever you want here. And so what he's been doing so far is a TFSI system and the FSI, but TFSI is the bulk material he's made so far. So, okay, what have we got? Well, Kwei comes along and said, Kwei, try and model this and see what you can get. Just get some understanding while we're waiting for this monomer to come. And so he modeled the system, and he found that comparing on the left-hand side is the model system, and at the bottom we have experimental TGs. We see that the ammonium versus phosphonium, definitely there is a significant decrease in TG in the pure polymer. You go from 371 to 295 in the MD simulation. That correlates to reasonably similar values in experiment, 383 to approximately 293, approximately K in DSC experiments. So that was nice. Again, we think we can trust the data because we have a similar TG to what we measure. And then in the 1 to 2 system with FSI, what he found was that the TG doesn't go down as much in the phosphonium system, but it does go down. Okay. On the right-hand side, we see, again, this co-coordination is not that different. It's a little bit lower. We do see from the, and I won't spend much time on this, we're still trying to analyze this data in more detail, but we do see from the radial distribution function, the coordination of the P-FSI or the N-FSI is a bit different. The green is the phosphorus and the red is the ammonium. So there are some subtle differences in the coordination, but we're still to try and understand exactly what's going on here. But it is promising to see that we can model the system and we determine the diffusion coefficient. So we say, okay, we can model it. Will it be a better system? So here we have the mean square displacement on the left-hand side. On the right-hand side, the extracted diffusion coefficient from the slope of these lines. We see that the blue and the green correspond to the phosphonium system. The other ones correspond to the ammonium, equivalent ammonium system. We have the TFSI mixed ion and the FSI. This is all, remember, in the MD simulation. But what's really interesting is that we're seeing a significant, almost a factor of 10, not quite. Here we go here. The diffusion coefficient of the DADMA is 10 to the minus 12. The phosphonium equivalent is 10 to the minus 11, an order of magnitude higher diffusivity. Now, will this correlate in reality? We'll show in a moment. And it does depend on whether it's TFSI or FSI, homoanions or mixed anions in the model. So that was interesting. That's promising, right? With phosphonium may actually give us better performance if we can make it at a reasonable cost and make it reasonably more easily. So Alex had come to Australia for some time last year and had a small amount of material with him, so measured diffusion coefficients of the system that he made, and all he had was the 1:2. We had 3 systems, 2:1, 1:1, and 1:2 materials with TFSI, FSI. And what he found then, which is really pleasing, was when I went back to the data, is that the 1:2 system, 80 degrees, which is where the MD simulations are done, is about 2 for 10 to the minus 11. What do we measure in the MD? About, where is it? The MD for the is about 3 by 10, MD 10 to the minus 11. So same order of magnitude. Similarly for the DADMA, same order of magnitude. That's very pleasing because with simulations are notoriously not necessarily accurate, but here we have we have good correlation. We see that the phosphonium system should have a factor of 10 higher diffusivity, or does, sorry, which should correspond to a higher conductivity and hopefully better performance in a device. That's still to come. That we don't have yet. I think in the last 5 minutes then, what I want to go back to the last few minutes is, okay, so we've made these materials. From a practical point of view, we don't have a freestanding film at this point in time. So if we really want to make these materials for a battery, we need to think about how we're going to make these freestanding. Some earlier work that I did with my team did with CSIRO on these, what we call pill block systems. These systems are different to the polydadma. The polycation is off this backbone. They're made from an acrylate root. And so if you're interested, there's publications on these systems if you're interested. But this acrylate route has proven quite challenging when it comes to the cathode stability. So it's not ideal, whereas the DADMA seems to be much more stable at the higher voltage, at the more positive voltages. And so whilst this works nicely, and CSIRO are currently doing a startup to try and commercialize this material, it's not ideal on the high voltage cathodes. So can we use the same technique though to try and make a nice material with the DADMA? And that's not as easy because the chemistry is different. The acrylate chemistry is quite straightforward to control molecular weight. Nevertheless, Antonella, who was working with David's group, she's now Technalia, but she worked in David's group at the time, and my then student Sneha spent some time at POLYMAT, and they did make a polystyrene tri-block with this polydadma, although we couldn't get very high molecular weight polystyrene. So the material is okay. It's not brilliant, but it is okay. And we use this material with sodium in that case, because Sneha's project was a sodium-based project, and she added different amounts of sodium FSI salt, and we found that, you know, as with the previous data we showed early on, that we got the TG did go down, although there was this parabolic type behavior again in this system, interestingly, which is a mixed system. And so she then measured, so Sneha then looked at the conductivity, and we can see we went as high as 70 degrees because if I go back to here, the TG of the second block, the polystyrene block, because it was low molecular weight, it actually was affected by the TG of the other block. So TG went down in the system. What this should do is not move. This should be an ionophobic block. It should not dissolve any sodium salt. It should not decrease the TG, but it did decrease, and we think that's because of it's a small molecular weight group. So that means that we couldn't go above 70 degrees without losing mechanical properties. Here we see then that conductivity at the 1:2 composition is almost into the -3, which is a factor of 10 higher than the lithium salt, as we saw earlier on, because the diffusivity of the sodium is higher. And again, she was able to show in symmetric cell cycling, quite low over potentials, very stable. And at the time, all we've done so far with this system is put into an NFP cell, which just to show that it did actually operate as a battery electrolyte, but we've got a long way to go still before we optimize the system, obviously. It's a very thick film, it's 250 microns, that will impact this behavior and in the full battery and also in the symmetric cycling. So we've got a long way to go still to optimize this, but I think it's fair to come back to my first slide and say there is a lot of space to play, space to play in these systems for solid state batteries, whether it's lithium, sodium, or any other metal system. So we've been playing in this space. We can improve things a little bit by adding a little bit of solvent or a little bit of ionic liquid. We can add another dimension and add maybe an inorganic filler or inorganic conductor and try and make composite electrolytes. There's a lot of room to play. So I hope with that I've given you a flavour of, and I'm not going to go through the summary just says what I've already been saying, so I won't go through the first dot points, just to say we've shown that we can make good materials with these cationic polyIOs. What we want to know still, however, is how important are the interfaces? How important are the interfaces between phases if you've got these molten salt-like phase versus the more molecular molten salt versus the polymer phases. If you have crystalline domains, how important is interface between the electrode and the electrolyte? How will the SCI be building up in these systems? And what other chemistries can we use? And can MD help guide us? Finally, I want to acknowledge the team at POLYMAT, our excursions last year out to the wine country, and my past team at Deakin University for all their efforts, and some specific people here that I've been acknowledging all the way along. And thank you for listening.
Yeah, we have plenty of time.